Okay guys, in this video lesson we're going to talk about our third and final law of motion, which is called Newton's third law. Okay. Looking at Newton's third law, let's actually take a step back. So the first law told us that an object in motion stays in motion unless acted upon by a force, or an object at rest stays at rest unless acted upon by a force. So that determined how things continually stay the same motion. Our second law talked about what happens if you do have a net force. So you apply a net force, that is going to equal to the mass times acceleration. So we're now figuring out how do we get things to accelerate. The third law takes a step back and kind of dives into this idea of more of a conceptual nature of what happens when you apply a force on an object. How does that object receive the force, and how does it apply forces back on you? Okay. The law stated says that for every action, there's an equal and opposite reaction. Okay. Another way of looking at that is all forces have to come in pairs. We call them action-reaction pairs. Okay. So when we look at this idea of action-reaction pairs, every time something is pushed on, for example, if you are a ghost on a skateboard and you push on the wall, okay, your hand pushes on the wall to the left, the wall must push back on you with the same amount of force to the right. Okay, that's an action-reaction pair. Okay, let's take a look at some reaction pair examples. Okay, we're going to go to this little website here called the Physics Classroom. They do a pretty good job of just explaining things at the high school level. So if you're ever looking at getting some extra help on stuff, the Physics Classroom is a good place to go. So Newton's third law, all right? We know that if you have an action, there has to be a reaction. So let's take a look at some examples of those things happening. Okay, a fish. Okay, so this one reads about a fish, but if you think about a fish, as a fish moves its fins back and forth, it pushes on the water. Now it's pushing the water backwards, so then the water then pushes back, propelling the fish forwards. Okay, so it's the same force, just equal and opposite. Birds are another example, okay? When birds flap their wings, they actually push down on the air molecules around them, okay? As a result, the air molecules push up on the bird, and the bird flies, okay? There's some aerodynamics in that too, but that's kind of the basics behind it, all right? The car one probably is the one that I want to spend the most time on because it might be not as easy to recognize, but at the same time, it's probably most useful for us because we're not a bird and we're not a fish, all right? If you drive a car, now the car is hooked up to an engine, and that engine causes the wheels to spin, right? The wheels spin in such a way that they actually grip the road, and they actually push the road backwards. Now, it seems kind of weird to think about that, but in perspective of what's going on there, if you said the car was not moving, if you focus on the car and said the wheels spin, you could say that the car stays still and that the earth moves backwards. Okay, it's a weird concept to think about, but it's valid, right? Now, since the car is pushing the road backwards, as a result, the road grips and it actually pushes the car forwards. Okay, so the wheels of your car are actually designed to pull the road backwards, causing the car to move forward. Okay, those are some action-reaction pairs. Now, if you're driving down a road and a firefly hits the windshield of a bus, okay. If we apply Newton's third law, what is greater, the force of the firefly or the force on the bus? Okay. Take a look at our answer. It's actually a trick question. Okay. When I ask you which one is greater, the force on the firefly or the force on the bus, the reality is each force is the same size, right? Newton's third law says every action is equal and opposite reaction, which means the forces are the same size. Now, that may seem kind of weird because there's no way that the bug feels the same amount of force as a bus. It does. The problem is the bug is tiny, okay? So the bug being so small, hitting a very, very big, massive bus, its acceleration is very different. So I'll show you what I mean by that, okay? So we have our bug here, and we'll call that bug, and we have our bus over here, okay? And since the forces have to equal each other, we can say that the force on the bug has to equal the force on the bus. Now, would you agree with me that the bug has a tiny little mass and that the bus has a gigantic mass, okay? So if the forces have to be equal to each other, And we know that force equals ma, and force equals ma. If we have a tiny little mass over here, that means the acceleration the bug feels is really good. That acceleration is so great, actually, it splatters the bug. It can't handle it. The bus, on the other hand, has a really big mass, so the acceleration it feels is tiny, almost negligible between the two things. So it isn't that their forces are different, it's the relationship between the mass that they have and the acceleration that they have is really what's causing our difference here. Okay? Space travel. Okay? A lot of times people think that once you get in outer space, you have to basically float around and not do any changes. That's not actually true. Okay? The way rockets work is rockets burn fuel, and they explode fuel, and that exploded fuel leaves the back of the rocket as a gas. Well, as that gas gets expelled out the back, what happens is the rocket then has to be pushed forwards. Okay, so you don't need wind or air or something to actually to fly through. When you get into outer space, the idea that you are propelling gases out your tailpipe basically means you get pushed forward. Action-reaction pairs. Okay. Now the gun one's another good one to take a look at, because when a gun, we have the same amount of force that happens. You fire the gun and the bullet comes flying out super fast. But the force the shooter feels against their shoulder is the same force that the bullet feels as it leaves the gun. Again, what's the difference? Well, the gun is very massive in comparison to the bullet. The bullet is very tiny. So even though they feel the exact same force, the bullet leaves with a much faster velocity because it was accelerated much more than the gun, even though the gun does kick backwards and into the shoulder of whoever the shooter is. Okay? And then our last one. Okay? We have two examples here where this person is pulling with 500 newtons of force. Okay? Where we have 500 newtons on the scale, I should say. So in both examples, we ask the question, is this person pulling with the same amount of force, or is the force he pulls here less or more when the elephant is pulling back against it? Okay? And again, if we take a look at the idea behind Newton's third law, then the third law says everything has equal and opposite. So if he is pulling with 500 newtons in that direction, that means the wall has to be pulling back with 500 newtons. Now it seems weird because the wall is just a brick and mortar. It's not actually pulling like you're with your hands, but its structural, its integrity that it has withstands a repulsive force from that of 500 newtons. So basically the ring doesn't pull out of the wall. No different than the elephant down here. The elephant does the same deal, right? The elephant just sits there and its friction holds its feet there, and you pull with 500 newtons and he pulls back just whatever he has to give you another 500 newtons. The thing is, the elephant's so massive, it just moves its mass back a little bit. It can generate 500 newtons really easily for that stuff. Okay? So that is Newton's third law in terms of action-reaction pairs. We can apply that to one more quick concept. If we drop a ping pong ball, does the Earth accelerate? Okay, little ping pong ball, drop it, let it go down. Does the Earth accelerate? On first idea, you'd probably say no. I mean, that seems kind of ridiculous that the Earth would accelerate when the ping pong ball is being dropped. But if we apply Newton's third law, the answer is yes. Okay? Every time an object gets dropped towards our planet and we accelerate towards the planet, okay, the planet has to accelerate back up towards it to counteract that because you have the force of gravity pulling it down, but the object has its own gravity that's forcing the Earth to move up. So let's take a look and see how big a difference that really is to us. All right? So we can say that the force that the planet feels has to be equal to the force of the ping pong ball feels has to be equal to the force the Earth feels, but opposite. That's why we have a negative sign in here. Okay? So the mass of the Earth times the acceleration of the Earth has to equal the opposite mass of the ping pong times the acceleration of the ping pong ball. If I rearrange this equation, I can solve for the acceleration the Earth feels. We just need some data. So a ping pong ball has a mass of 0.0027 kilograms. Not very heavy, okay? Multiply that times a negative 9.81. That's the acceleration that the ping pong ball will feel. Divide by the mass of the Earth, 5.97 times 10 to the 24th kilograms. And if we solve for that, we get 4.4 times 10 to the negative 27th meters per second squared. Okay, so imagine this 4.4 has 26 zeros in front of it. Okay, this value in acceleration is less than the size of an atom in terms of mass. Okay, so it's tiny. It's really, really tiny. Okay, but it does exist. Okay, now do we feel this? No. Even if we dropped like a whole huge tanker ship off some cliff and as it fell to the earth, would we, you know, see a vibration or a shift in our earth? No. It's negligible in our perspective, but it still exists. It's still there. It's just not big enough for us to notice it or deal with it. Okay, and it applies Newton's third law. All right. We're going to end the video here. In our next video, we will take off and start talking about friction, how friction works. Thank you.